So last class period, we were in 3.3, and we were talking about power functions and polynomials. Remember when we say power functions, we just mean functions that look like, we said k, I can't remember now. Yeah, k x to the p. Where p is any number. Okay. And we talked about what's called the end behavior of these power functions. When p is a whole number and odd, we know one side goes off to infinity and one side goes off to negative infinity. When p is a whole number and even, well, then both sides are going to infinity or both sides are going to go to negative infinity, right? That's kind of what we looked at last time, depending on whether k is positive or negative. Okay. And then we said, well, polynomial functions are functions that can be written like this: a sub n x to the n plus a sub n minus 1 x to the n minus 1, and so on and so forth, till you get a1 x to the first plus a sub 0, which is our constant. Here, our a sub n was not 0, but n is a whole number. And the very last thing we did was we looked at the degree of the polynomial, the leading coefficient, the leading term, all of which were determined by a sub n x to the n. Now, one thing I didn't mention last time that we will this time, let's say we want to state the degree and lead coefficient of the following polynomial function. Let's take 5x to the third minus 8x plus 7x to the fourth minus 13. Again, this is similar to what we did last time. Now, in this scenario, what is the lead term? Not exactly. Sorry. Yeah. This one's it's the trick one, right? Where most of the times we write polynomials in descending order, so they go from highest degree to lowest degree terms. That's what generally we do. But there are these weird occasions in which they have things that are not in descending order. So just be careful about that. If things are not in descending order, and now I've written things in descending order, go ahead and write them in descending order, or just look at it and say, oh yeah, that's not in descending order. Once you write things in descending order, then you can say the lead term is 7x to the 4th. It's the one with highest degree. And therefore the lead coefficient is 7, and the degree is 4. Again, the vast majority of times when people write polynomials in math, we like to write them in descending order. But there are occasions in which polynomials might be written not in descending order. So that's all I wanted to mention. So just be careful of that. Now, obviously, when you look at polynomial functions and you compare to power functions, if the power was whole, would be just one-term polynomial functions, right? Obviously, the power could be anything. Could be 1/2 or could be 0.7. But because of this connection, the end behavior of polynomial functions is going to be similar to the end behavior of power functions. So let me say it this way. End behavior of polynomial functions is determined by the leading term. The term of highest degree. That leading term is essentially a power function, right? And so the behavior of the leading, the behavior of the power function at the end is going to be the same as the end behavior of the polynomial. So the end behavior of the polynomial is the same as the end behavior of the power function of the leading term. That makes sense? So let's actually, we'll go back to the same polynomial here. And let's determine the end behavior. Of f of x equals 7x to the fourth plus 5x to the third minus 8x minus 13. That makes sense. So we'll determine the end behavior of this. Well, what we're saying is that it's the same as the end behavior of, I'll call it P of x for power function of x, which is equal to 7x to the fourth. So we know as x goes to positive infinity, my function is going to go to something. And as x goes to negative infinity, my function goes to something. By the way, do we all remember what 7x to the fourth does? Power function wise. X to the fourth, we have an even power. 7 is obviously positive, so even power, positive coefficient. It does a coming up of some way, shape, or form. So as x goes to infinity, meaning as we go to the right, the function's going up forever. As the function goes to the left, as we travel to the left on this curve, the function is going up forever. And that's it. That's the whole thing. Now, let me be very, very clear here. This is the end behavior. All right? In reality, this function here may not look like a perfect U cup. Does that make sense? This function here might do all kinds of wacky things in the middle. So it might go up and down and, do something like that in the middle, right? But the end behavior is like that of 7x to the fourth. So we don't know what's going on in the middle unless we graph it, of course. So it might do all kinds of crazy stuff. But I know the end is going to look like the end of 7x to the fourth. So going to go up and to left. Does everybody understand why it has to be that way? Why 7x to the fourth has to be determining the end behavior as x goes off to infinity? Well, think about these terms and which ones are going to be bigger. If I compare a term with x to the fourth in it with x to the third, and we plug in a really large number. Now let's just plug in 1,000. Well, x to the fourth, if I plug in 1,000, is going to be 1,000 times bigger than x to the third. Now plug in 1,000,000. Well, x to the fourth, if I plug in 1,000,000, is going to be 1,000,000 times bigger than x to the third. And that's just with 1,000,000. Think about plugging in 1,000,000,000, trillion, right? Think about going even higher than that, going off to infinity. As you plug in bigger and bigger and bigger numbers, this term is going to be way bigger than any of these other terms. And so the x to the fourth term is going to dictate what the entire function does, because it's going to be so much bigger in comparison to all those other terms. All right, bigger in terms of absolute value. Does that make sense? So that's the idea. Let's do another. I want you to try this one on your own. Again, same in behavior. So determine in behavior. What was g of x this time? G of x equals -3 x to the fifth plus 6x to the fourth minus 7x squared plus 8x minus 2. All right, so let's do this. -3x to the fifth is the leading term. So the end behavior of that polynomial function is the same as the end behavior of polynomial function equal to 3x to the fifth. Now 3x to the fifth, we know is going to start in the upper left, and then as you move right, travel down and go down forever. Again, my g of x is not gonna necessarily, it's gonna have some weird stuff in the middle here. Who knows? Might have some weird stuff in the middle. But the end behavior, as we move to the right, we're going down towards negative infinity as you move towards the right. Going down. And as you move towards the left, you're going up towards positive infinity. So this is the behavior of this polynomial function. All right. Now, let me share with you what the actual graphs of those things look like, the things I had on the board. Polynomial. This will lead us right into 3-4. 3-4 and 3-3 are very similar. So let's go f of x equals, I'll do the first one we did, 7x to the fourth plus 5x to the third. Minus 8x minus 13. There we go. So you see it doesn't have like a smooth cup shape. It has kind of a shape on the left here. And then it does kind of a weird, almost linear thing. That's not exactly a line, but don't get me wrong, that's not a line, but that's some weird shape there. Then goes back up. But yeah, almost looks linear. Hits the bottom, goes back up. So again, if we ignore kind of the bottom shape, what's it look like? It looks like cup pointing up, right? And then the other, negative 3x to the fifth, plus 6x to the fourth, minus 7x squared, plus 8x minus 2. There we go. Again, we get some really awkward looking shape in the middle. But if I scroll out and ignore the middle, what's happening? Well, to the left, going off to infinity if I'm moving left, going off to negative infinity if I'm moving towards the right. Okay. But again, you get some awkward looking shapes in the middle here. So that's my point, is that, yeah, the middle may look all kinds of different ways, but the end behavior is determined by that lead term. Okay. So that's just graphically. By the way, notice that this negative 3x to the fifth crossed the x-axis in 3 different places. So it had 3 different x-intercepts, right? This leads us into 3-4. But there's a little bit of 3-3 and 3-4. It's very, very mixed. They cover kind of both topics in the same, well, in the same vein, I guess. So let me start just by introducing what 3-4 is going to do. 3-4 is going to talk about the graphs of polynomial functions. All right. There's going to be two big takeaways on this. One is, what do the graphs of polynomial functions generally look like? And the other will be using some of those facts to do finding zeros and something called intermediate value theorem. It'll make sense later. Okay. So let's talk about some of the properties of polynomial function or of graphs of polynomial functions. All right. So we have a polynomial function. What is the graph? What are going to be the properties of that graph? Well, one of the properties of that graph is that all polynomial functions are continuous over the real numbers. So property number one, the graph is continuous over the real numbers. That means there's no big gaps or there's no jumps. As you draw it, you'll never like stop one place and then jump down and start drawing another place, right? Also, there's not going to be any holes in the graph. So these two things can't happen. You guys get what I'm saying there? So it's continuous. You can draw it all smooth. Okay. Also, polynomial functions actually have no sharp corners. You know, like our absolute value function had a v. That's never going to happen in a polynomial. Now, a polynomial may have a graph that looks down and turns up fairly quickly, but if you zoom in, it's always going to turn up like this, like a U shape. Everybody follow? Not like a sharp corner. So it's going to have U shapes, no sharp corners. Here's one. At most n, x intercepts. When I say n, we're talking about the degree of the polynomial. So the degree of the polynomial determines how many x-intercepts at maximum I can have. You can have at most n x-intercepts if it's degree n. Now you could have fewer, right? We just saw on Desmos a polynomial function of degree 5, which had 3 x-intercepts. Remember just seeing that? So we just had a degree 5 polynomial with 3. So there could be fewer. And the same thing here. When we graph this one, this was degree 4, but if you looked at that graph, there was only 2 x-intercepts. And then we already know this. As far as the end behavior, it either increases or decreases as x goes to infinity or negative infinity. I'll just do plus or minus infinity. Does that work? So I'm talking about the end behavior. End behavior shoots off to infinity or negative infinity, depending on that lead term. All right. Now I want to mention or discuss graphs and polynomial functions. So we'll look at this. So this was the degree 5 polynomial we had up earlier. All right. Zooming into the most interesting section. As you move to the left, it just shoots off to infinity. As you move to the right, it shoots off to negative infinity. So this is the most interesting section of the graph. You'll notice that we have, like I said, 3 x-intercepts. Those are kind of ugly numbers, so we'll worry about where they come from now. But if we had to identify those, we could just look at a graph and say, yeah, the x-intercepts are the points where my hits the x-axis. I want you to look at these 2 points as well. Right. Those 2 points also have special names, and they are called turning points. A turning point is where my function goes from decreasing to increasing or from increasing to decreasing. So as you see, at this point, if I am to the left of that point, my function is decreasing. Once I hit that point, my function starts increasing. I start increasing until I hit this point, and then my function starts decreasing. So that's called a turning point, where your function goes from increasing to decreasing, or decreasing to increasing. And at those turning points, we're going to have sort of the smallest value or the highest value in that area, right? Let's take a look at the first equation that I had. Again, here's the interesting section. We have 7x to the fourth plus 5x to the third minus 8x minus 13. You'll see this one has two x-intercepts. In this case, they're not at very nice numbers, but we can see where they're at. And it has one turning point. Where we go from, in this case, decreasing to increasing. Let's take another. I'll do x to the third minus 1x squared minus x. So here we go, x to the third minus, actually do minus 2x squared minus x. X to the third minus 2x squared minus x. You'll notice that if you zoom into the most interesting part, you get 3 x-intercepts. And then 2 turning points, right? Now, what I'm trying to get at, and this is probably a bad 3 examples because each one of them was exact, but let me do another example. Ready? Let's take minus 4. How many x-intercepts do I have now? Just the one, right? Way up there. How many turning points do I have? 2. Still 2, right? Okay. So the number of x-intercepts, the number of turning points, there's not always one less, is what I'm trying to get at. Okay. In the 3 examples I had before, there was one less. But I will say this. How many turning points can a function with degree 3 have? Well, it can have at most, turns out, 2. Might have fewer. How about a degree 5? Well, a degree 5 can have at most 4 turning points. How about a degree 4? A degree 4 can have at most 3. This one doesn't have 3, just has the 1. But it can have at most 3 turning points. That makes sense? So, if can have the most n x-intercepts. We know it decreases or increases as we go off to infinity. And has at most n minus 1 turning points. And by the way, if you have 3 turning points, it doesn't mean there's 4 x-intercepts, right? You can have 3 turning points and only 1 x-intercept if you want. Something like that. Okay. Wanted to mention that about turning points, that turning points are really these things where the graph is going from increasing to decreasing or decreasing to increasing. And we can have at most n minus 1 of those in a polynomial of this type. Is that okay about graphs and polynomial functions? All right. Now, we're going to focus on finding zeros of polynomial functions, which is the same thing as finding the x-intercepts, right? So, finding x-intercepts is finding points on the graph of the form, I was going to say where, form x comma 0, right? X-intercepts have zeros in for the y value. Okay. This is also called finding the zeros of a function. A zero of a function is a value we'll call it Z for 0, such that when you plug in that value into the function, you get out a 0. So the 0 of a function is really the x value of an x-intercept. Did you follow that input-output stuff? Factoring in that. Okay. So let's find x-intercepts or find zeros of a function. Now, the fact is that 3, 4 and 3, 5 and 3, 6 are really all about finding zeros of polynomial functions. Okay, so the rest of 3, 4, the rest of 3, 5, the rest of 3, 6 are essentially all about finding zeros of polynomial functions, which is the same as finding the x-intercepts. Okay. So there's a couple of different techniques. The one that we're going to see in 3, 4 in this section is factoring. So we can find x-intercepts by factoring and using the zero factor property. This is going to be sort of option number 1 for finding zeros. So let's say we want to find the zeros of this polynomial function. And I'm going to write it as have already been factored. So let's take x minus 4 times x plus 8 times x plus 1 times x. So if I want to find the zeros or the x-intercepts, I want an output to be 0. So I just plug in 0 in my output. The right-hand side has already been factored for me. And just like when we were dealing with quadratics, and we were factoring and solving quadratic functions, if I have 0 equals a bunch of factors multiplied times each other, then any of those factors could have been set to 0. And just like a quadratic, since I had, back in the quadratic, I'd have usually 2 factors set equal to 0. Here I have 4 factors set equal to 0, but I can solve each individual equation. That's my point. And so add 4 to both sides, you get x equals 4. X equals -8. X equals -1. And then x equals 0 as the 4 zeros of that polynomial. Which means that the x-intercepts occur at the point 4, 0, at the point -8, 0, at the point -1, 0, at the point 0, 0. So those are the x-intercepts, right? So if we can factor, then we can find the x-intercepts, or we can find the zeros by using factor. Let's do another. Let's find the x-intercepts of, we'll call it g of x equals x to the third minus 8x squared minus 20x. First thing I'm going to do is set y equal to 0. Now, in this case, I can factor out a greatest common factor. So I'm going to factor a greatest common factor of x out. I'm left with x squared minus 8x minus 20 in the parentheses. And then I can factor this quadratic, just like normal. So I factor that quadratic, factors of -20 that add to -8. I think a 2 and a -10 is the 1. So this factors into x times x plus 2 times x minus 10. And now I'm at the same place I was earlier. I can set each of those factors equal to 0. X equals 0. 2 equals 10. And then solve all three. the idea of finding zeros using factoring. Okay. So we're finding zeros using factoring. Questions about that technique in particular? All right. Let's do another one. Let's take find the x-intercepts by factoring this. We'll take my function to be 2x to the third plus 28x squared plus 98x. I want you to go try that one on your own. All right, let's take a look at this one. So first thing we're gonna do is set y to be 0. Set your output to be 0. That's every time you're looking for x-intercepts or every time you're looking for zeros, you're gonna set your output to be 0. Then, in this case, the first thing I always look for is greatest common factor. This case, greatest common factor is 2x. When I factor out a 2x from each term, I'm left with x squared plus 14x plus 49. X squared plus 14x plus 49 is a polynomial, which is quadratic. And we've dealt with quadratic. We've dealt with quadratic functions before, quadratic polynomials, and dealt with factoring. So we can do factors of 49 that add to 14. Well, they're both 7. So I get 0 equals 2x times x plus 7 times another copy of x plus 7. So either 2x is equal to 0, right this way, or x plus 7 is equal to 0, or the other x plus 7 is equal to 0. Now, you don't have to repeat your equations if you don't want. By the way, dividing both sides by 2, you get x equals 0, or x equals -7. This is also x equals -7, obviously. That means we have 2 x-intercepts. One at the point 0, 0, and the other at the point -7, 0. We'll talk about this later, but the fact that -7 showed up as a solution 2 times means that -7 has what we call multiplicity of 2. Okay? Just means how many times did it show up as a solution. So -7 is an x-intercept. It's a 0, but technically it has a multiplicity of 2. It's good. And the previous one, all of these had multiplicity of 1 because they showed up just once. Previous problem. Now, graphing wise, I've typed in both the first and second one we just did. So if you were to have graphed this x to the third minus 8x squared minus 20x, you've gotten cubic that looks like this. Might be hard to see. But that was the first one we did with x-intercepts at -2, 0, and 10. That's what that looks like. So at the point 0, 0, -2, 0, and then 10, 0, it's like that. The other, the one we just did, which had x-intercepts at 0, 0, and then -7, 0, looks like that. Notice that x-intercept at -7, 0 is also the turning point. Or it's also a turning point, I should say. So that multiplicity 2 made it so that it's a turning point. Any questions about that? The graphs and all this goes. These ones were really stretched out, obviously. That's okay. All right. Good. Now, these two equations, they were able to be solved by just factoring out the greatest common factor. And then we had a quadratic remaining. So that's a good place to start with factoring if it's not just quadratic. If it's just quadratic, then we already know how to factor, right? We've factored a lot of those. But if it's like this, to a third degree, also known as cubic, we start by looking for a greatest common factor. Pull out the greatest common factor, and then factor the remaining quadratic, right? That's the technique we've done so far. Another technique is one like this. Solve via factoring. I'm going to start with a cubic third degree. Now I'll start with this one. This one is a little bit more straightforward. I'll solve another one in the back. So this is going to be a different technique than we've done so far. So I want to introduce you to this different technique. So obviously we have 4 terms here, and there is no greatest common factor amongst the 4 terms. All right. One thing you could try, and this is what we're going to do now, is if you have something like this, you could try to pair, oh shoot, let me first set this thing equal to 0, obviously. Otherwise it's solve via factoring, you should say. You find x-intercepts. But find zeros, it doesn't matter. So first thing, set it equal to 0. Sorry. I'm gonna step ahead, but you guys know where we're going with this. So we're finding zeros still, trying to find x-intercepts, trying to find zeros still. So we're gonna take, if I have 4 terms, there's a unique technique which says, let's pair the first 2 and pair the second 2. And then what I'm going to do is I'm going to pull out a greatest common factor amongst the first 2. X to the third and x squared. I have a greatest common factor of x squared. So if I pull that out, I get x squared times x minus 1. And then I can look at the second two terms. And I can say, well, out of 16x and 16, greatest common factor is 16. Now, this is a minus 16 on this first one. So I'm going to pull out a factor of negative 16. So that my first term that remains is positive. So if I pull out a negative 16, this first term just becomes an x. And if I pull out a negative 16, the second term becomes a negative 1. Now this is the really unique case in which I can keep going. Because when I factored out the first two, and when I factored out of the second two, I got the exact same parentheses right here. Because I got those exact same parentheses, what I can do is I can say, well, actually, this is the same as x squared minus 16 times the quantity x minus 1. Do I see that? If I were to multiply these two polynomials out, I would have taken x squared times both terms, is this, and then minus 16 times both terms, which is this. And now x squared minus 16 can factor because it's a difference of perfect squares. It's kind of like saying, what are the factors of negative 16 that add to 0? Because we have no middle term. So factors of negative 16 that add to 0 are negative 4 and positive 4. The difference of squares factors into x minus 4 times x plus 4. And then I have this x minus 1 tacked on at the end. Now I'm at the same place I've been the last few. So I can simply just set each factor equal to 0 and solve. So the zeros are 4, negative 4, and 1. That means the x-intercepts are 4, 0, negative 4, 0, and 1, 0. Any questions about that? That's a interesting scenario. Questions? Good? Good with that technique? That's an interesting technique, but it can work sometimes. Let's do another one of those techniques. So let's take g of x is equal to x to the third minus 5x squared. Let's do minus 9x plus 45. I want you to try this one on your own. Okay, everybody got this? So let's go through that technique. 0 equals, pair the first two, pair the second two. When I pair the first two, I can factor out a greatest common factor of x squared. When I pair the second two, I can factor out a greatest common factor of I'm gonna factor out a -9 or -9. And if I factor out a -9, then the things inside my parentheses match perfectly. So I can rewrite that problem as x squared minus 9 times x minus 5. Difference of perfect squares can be factored into x minus 3 times x plus 3. And I still have the x minus 5 tacked on. Any of those terms could be set equal to 0. And then solved. And so if you're asked to find the x-intercepts, we have 3 of them. The x-intercept 3, 0, the x-intercept -3, 0, and the x-intercept 5, 0. Just so you know, when you type these things into Moodle, and if you have 3 x-intercepts to write, it'll say, write the x-intercept with the biggest x value first, and then the second x value second, and then the smallest x value third, or vice versa, something. It'll go in order. But it'll explicitly say biggest x value, smallest x value, middle x value, something like that. Now, this technique here really only works in very, very special circumstances. Circumstances where we have this difference of squares as a factor. Okay. That's why this special technique worked in this case. We had a difference of squares as a factor. Usually that doesn't happen. In fact, usually we can't even factor. If I just give you a bunch of random coefficients to an x to the third, factoring may be very, very hard. Okay. So don't think that's going to always work out in every single x to the third polynomial function with 4 terms. It's not always going to be able to be solved this way. In fact, usually it won't be. So, what are some other ways we can look for zeros? Well, one other way to look for zeros is start by looking for areas in which zeros exist. Could exist. Now, there's a thing called the intermediate value theorem. It says if I have a function, we'll call it f of x, is continuous. So if a function is continuous, on a certain interval containing a and b, I'm not gonna go into all that stuff, but let's just imagine it's continuous everywhere, because that's what we need here. Then for every y value such that we'll call it this. You could have these in the other direction. I'm not saying A always has to give you the smaller. You could have these in the other direction, doesn't matter. But I'll write it this way. Then for every y value, there exists an x value between A and B such that when you plug in that x value, it gives you the y value you want. Now that's kind of this is a harder linguistics experiment than it actually is a math principle. Here's the math principle. You have a point down here. You have a point up here. And there's some y value. Now, y values are horizontal lines, right? So there's some y value here. If your function is continuous, all we're saying, if my function is continuous between A and B, that means my function has to cross the line at some point between A and B. Can you follow that? So if I draw a horizontal line and then I draw the function, if it's continuous, it's got to cross the line. Now, it may cross the line once. Could cross the line twice, right? Could cross the line a few times. But it's got to cross the line at least once. That makes sense? As long as it's continuous, it's got to cross the line. You can't jump. You have to draw it without lifting your pen, your pencil. And it is a function, so we can't like go back and forth, go around the line or do anything like weird like that. So if we have a continuous function, it has to cross this vertical line. Or excuse me, I say vertical, horizontal line. Now, what horizontal line are we very accustomed to? Well, the x-axis, right? The line y equals 0. So that means this intermediate value theorem is going to say if one of the outputs is negative, one of the outputs is positive, then it's got to cross the x-axis at some point. Okay. So for us, if we have a function that's polynomial, we know polynomials are continuous. We mentioned that earlier. So polynomial functions are continuous. Are continuous. So if polynomial function we'll call it f of x as f of a, which is negative, and f of b, which is positive, then f of x must cross x-axis between somewhere between a and b. At least once. Could be more. So that all comes from intermediate value theorem. And intermediate value theorem, again, is just the principle. If you have a continuous function and you know 2 points on opposite sides of a horizontal line, it's going to cross that horizontal line at some point in between A and B. And again, I always get it with this one lower and this one higher, but it works the same, obviously, if the first one is higher and the second one is lower than the horizontal line, right? So it works the same, whichever, if you start higher and then lower, or if you start lower and higher. So let's take the following function. And I'll use P for polynomial function. Polynomial function, x to the third minus 2x squared plus 1. Okay. By the way, if you try to factor this, it's not going to factor very nicely. Not over whole numbers anyways. So I want you to do this. I want you to plug in -1 into this polynomial function and see what you get. And then let's plug in 3 into this polynomial function and see what we get. So when I plugged in -1, I got -2 as the output. When I plugged in a 3, I got a 10 as the output. So from what we just saw earlier, this means at least 1, 0, we'll call it Z, between -1 and 3. So in other words, there's gonna be some 0 in that region. At least 1. There could be 2, or it could be 3, it could be. How about this? I want you to plug in -1. We already did that, so we got -2. I want you to plug in 0 and see what you get. And then say, is there a 0? Does this imply there's a 0 between -1 and 0? And then do the same thing by plugging in 0. See what you get. And plugging in, let's do a 1. See what you get there. Oh, I'm sorry, I didn't want to do 1, excuse me. I want to do 2. Okay. So when you plug in -1 and then you plug in 0, that means there has to be at least 1 0, or maybe it's easier to think of this as x-intercepts, but at least 1 x-intercept whose x value is between -1 and 0. Right? That, in other words, is saying at least 1 0 between -1 and 0. Now, if you plug in 0 and plug in 2, you get a 1. Does this guarantee that there's no x-intercepts between 0 and 1? No. This actually guarantees that there's at least 0 x-intercepts. Does that make sense? You still could have like 2 points on the same side of the line of the x-axis, and then do something like that, obviously. That makes sense. But we're not guaranteed. Okay? So the way we phrase this is we are not guaranteed an x-intercept between an x value of 0 and an x value of 2. I'm trying to write these in different ways just so you see that there's a number of different phrasings people can use that mean the exact same thing, right? So there's a 0 between these values, there's an x-intercept between these values. And so I'm trying to write in a few different ways. They all mean the same thing. It's just a matter of which we prefer. All right. Interestingly enough, I did graph this exact polynomial function. And what you'll see is that this polynomial function, in fact, does have 3 x-intercepts. One, just like we knew, is going to be between -1 and 0. But if you look at between 0 and 2, while we're not guaranteed an x-intercept, this one does go down and touch the line twice between 0 and 2, come back up. That makes sense. So we're not guaranteed one, but in this case it did. So obviously if we change the polynomial just slightly, we have no x-intercepts, right? Between 0 and 2. But this one, the one I had originally written, did in fact have 2 x-intercepts there. So the guarantee is just that. It's a guarantee that there's at least 1, but sometimes a guarantee of at least 1 means there might be 3. Like in this first example, we had going from -1 to 3. -1 was down here, 3 was way up there, and we were guaranteed to have 1 x-intercept in that region, but we ended up with 3. All right. Any questions about that? I don't think there's much else to say. But just guarantee, does it have to have a 0 or does it not? Does it, again, this says it does not have to have a 0 there. All right? Because they're on the same side. Both positive outputs. All right, everybody get the intermediate value theorem? So sometimes that intermediate value theorem can kind of narrow down the range of what we're looking for and where we're looking for zeros. Okay. Excuse me. Now, the next step in finding these zeros is dividing polynomials. All right. And in particular, we're going to divide polynomials using log division and synthetic division, but we're going to divide a specific type of polynomial, right? We will divide the polynomial by x minus r. Why do you think we're going to use x minus r there? Well, because that's hopefully what I get my factors into, right? Hopefully I can get my factors into x minus r, something like that. So let's do this. Let's divide using long division. Let's take x to the third minus 2x plus 1, and let's divide it by x plus 2. And I'll use long division. Yeah, I'll do x plus 2 first. Now, I don't know if you remember how to do polynomial division by long division. But what you do is whatever you're dividing by, okay, that's your divisor. So you're going to take your divisor and you're going to put it out in front of that division sign. And inside the division sign, you'll put what's called your dividend, right? Dividend, divisor. These are not words you have to memorize or anything like that. And what we're going to do is we're going to make sure each term is represented. Now you'll notice we have an x to the third minus 2x plus 1. Oh, I'm sorry. I want to do 2x squared plus 1. I want to have the same. You guys okay with that? 2x squared plus 1. I wanted to have the same as what we did last time. Minus 2x squared. Now be careful about this. I don't have an x to the first term. So underneath the sign, I have to put basically a 0 x to the first term. And then plus 1. You guys remember doing something like this? Good. So then I say, I need an x to the third term, and I have an x. What do I multiply x by to get x to the third? X squared. So I multiply x squared by both pieces, x times x squared becomes x to the third. X squared times 2 becomes 2x x squared. Now be careful about this. It's not 1, 2, yeah, that's what I think too. When we do that, so x squared times x squared times 2, and then I'm going to subtract this whole line. I get negative 4x squared plus 0x plus 1. That 0x, again, I just want to be there for a placeholder. Then I ask, what do I need to multiply x by to get negative 4 times x squared? And I need to multiply by a minus 4x. Negative 4x times x gives me negative 4x squared. Negative 4x times 2 gives me minus 8x. I'm going to subtract this once again. That'll cancel out my x squared terms. 0x plus 8x gives me a plus 8x plus 1. And then I ask myself, again, what do I need to multiply by x to get this first term here? The answer there is 8, and that's a positive 8. 8 times x is 8x. 8 times 2 is 16. Subtract the entire polynomial. And then I get minus 15. Okay. Does that work? So what we're saying is that if we take x to the third minus 2x squared plus 1 and divide it by x plus 2, I end up with the polynomial x squared minus 4x plus 8 with remainder of negative 15. You know another way to write that? Another way to write this instead of writing a remainder is to say this is like plus negative 15 over x plus 2. That remainder is just like what part of the x plus 2 I'm going to use. So it's like a numerator in my fraction. Is that all right? Long division? Let's do another long division. Did that yet? I don't think so. I think I want to do something else. Let's do x to the third plus 8x squared minus 5x plus 1, all divided by all divided by x minus 3. Go ahead and do this one on your own. All right, let me go through. I think we can get this. There's going to be a quicker method, so if you're not very fast at long division, that's good. Most people aren't. Long division takes a minute. So let's take a look. I need to get an x to the third. I already have an x, so x squared times x gives me x to the third. When I multiply x squared times x to get x to the third, x squared times -3 is minus 3x squared. Subtract that whole thing. I get 11x squared minus 5x plus 1. Now I need to get 11x squared. So that's plus 11x that I need to have on top. 11x times x gives me 11x squared. 11x times -3 gives me minus 33x. Subtract that whole thing. I end up with 28x plus 1. Then I have to say I need a 28 up top. 28 times x is 28x. 28 times -3 is, what's that, 84? -84. Is that right? Is that in my head? And then subtract the whole thing. I get a positive 85 as my remainder. Okay. So this long division is x squared plus 11x plus 28 with remainder 5. Now, the issue with doing things always with long division is it just takes time. Okay? And it takes a lot of writing. So there's another division that we can do, which takes a little bit less time. So if we want to do long division, we can do it. We can do it that way. But when you're dividing by x minus a number, we can use synthetic division. I'm gonna erase this real quick. So long division takes a long time. Used when dividing by x minus r. You're going to ask why do they always keep using lowercase r in there? And it's because it's connection to another word that I'll talk about later. So here's how that works. When I'm dividing by x minus r, let's say I have a polynomial divided by x minus r. In synthetic division, we're going to sort of set the r aside. And then I'm going to write the coefficients of the polynomial on top. I'm going to create a space in here. All right? And we're going to have something on the bottom. And in each subsequent iteration, the first coefficient is going to drop down. You're going to get whatever a sub n is, right? Coefficient of the polynomial. And then you're going to take r times that. So we're going to do r times a to the n. And then you're going to add and you're going to get some new number here. You're going to add the second coefficient to this one. You get some new number. I don't know, what do you want to call it? We'll just call it new number. We'll call it M1. And then you're just going to keep doing that over and over and over again. R times this one. Then you're going to add. And then you're going to get some M2. And you just keep doing. Every time you times R. And you do this process all the way until you get rid of your polynomial. And what you're gonna get is that your polynomial divided by x minus r is actually a n times x to the n minus 1. That always happens. You lose a degree. Okay, follow that. Plus m1 x to the n minus 2 plus, and you just keep going on and on and on till you get to the end with remainder. Whatever the blank, I don't know what's gonna, these numbers, okay? That's the best way I can describe it without using numbers. It's gonna be much easier to think through once we have numbers. All right. So let's go back to this example here. We had x to the third minus 2x squared plus 1 divided by x plus 2. And we're going to divide that using synthetic division. All right. So that same problem I'm going to do now with synthetic division that I had on board. Okay. So what I have to do is I have to set up my r. Now, be careful here. This is an x plus 2, but remember, in synthetic division, it's x minus r. So what's my r here? Not a 2, it's a negative 2. Everybody follow? So it's a negative 2. Now let's put the coefficients of this polynomial. The x to the third term is a 1. The x squared term is a negative 2. The x to the first term is a 0. And the constant is a 1. I'll leave some space. And this is what I do. I drop the 1 down. I get a 1 here. I take negative 2 times 1. Now the negative 2 is coming from this guy over here. All right. So we're timesing by negative 2. 1 times negative 2 is another negative 2. Then I add those two. Then I take, and again, I multiply this number, this negative 4 now, by a negative 2. I would get an 8. And then I would add those. I take my 8, I multiply that by a negative 2. That would give me negative 16. And then I would add those. So my last one is adding 1 plus negative 16, and now I'm out of columns here. Now, by doing this on top, my top polynomial, this was the coefficient of the x to the third term. On my bottom polynomial, we drop all of them by 1 degree. We drop every term by a degree. And this last one that used to be a constant, that becomes the term that's gonna be my remainder. You follow? So this tells me that x to the third minus 2x squared plus 1 divided by x plus 2 is actually 1x squared minus 4x plus 8 with remainder of negative 15. That's exactly what we got earlier, right? But once you learn synthetic division, it just becomes much, much quicker to do than the long division. All right? Let's do another one. This one we haven't done yet. So let's take x to the third minus 4x squared plus 3x minus 7, all divided by x minus 6. All right, this will be the last one we do. I'll show you how fast this goes. So we're dividing by x minus r. And my r here is a 6, right? Because we have x, it's always x minus r. Gotta be very careful about that. 1, -4, 3, -7. Those go in order. So now I'm ready to work this. 1 drops down, becomes a 1. I multiply times 6. 1 times 6 is a 6. Add those two up, I get a 2. 2 times 6 is a 12. Add those two up, I get 15. 15 times 6 is, I believe, 90. Add those two up, we get 83. So just like that, I know that x to the third minus 4x squared plus 3x minus 7 divided by x minus 6 is equal to, remember this started as x to the third, so this is going to start with x squared. So that's 1x squared plus 2x plus 15 with remainder of 83. Like I said, once you get good at the synthetic division, then it goes a lot quicker than long division. Now remember, the downfall of synthetic division is that it only works with x minus r. Only works with x minus a number. If you are dividing by some other thing, some other polynomial, let's say you're dividing by 2x plus 5. Synthetic division is not going to work as easily. You have to manipulate it. If you're dividing by like x squared plus 3x minus 2, then you're going to have to turn to long division in that case. But if you're dividing by x minus a number, synthetic division works really, really nicely. Okay. Now the big tools of this section 3-5 are done with. Now we know how to divide. We're going to point out some interesting facts about this whole division and the relationship between division by x minus r and finding x-intercepts. next time, okay? So this will all tie into finding x-intercepts again, and zeros and things like that. That work? All right, I will see you all next time. Thursday, or Wednesday, that's it. Wednesday.